Yeah, so as they say in Monty Python, and now for something completely different. Not quite, but actually piggybacking on that. So it really sets the stage, right? We're exploring for water. And so this is actually an instrument that could be used to help sort of understand not only the surface composition of the regolith on the moon, but also investigate the presence of water, especially in permanently shadowed regions. And so I just want to acknowledge my co-authors, and this is AMIM instrument that we have been developing at APL, initially under Picasso grant, but most recently under a NASA DALI grant. Okay, so why do we care about microscopic imaging and why it's so important? And so things that we've learned over especially with the Mars exploration rovers and subsequent missions, right, that really being able to investigate planetary surfaces at the microscale is really essential, right? And of course, now almost every mission whether it's going to the moon, Mars, and even in the outer planets, right, they're going to have really compact instruments, but also microimagers. And so one of the advantages is that these microimagers really significantly enhance science return by supporting sort of real-time hypothesis-driven exploration. And so, and we're really looking forward to, especially with Viper mission coming up and for example, Lunar Vertex as well. Okay, so AMIM is basically an instrument, if you think about like M cubed, but you shrink it and you apply it at the microscale, right? And so it combines microscopic imaging with microspectroscopy that allows you to really map mineral grains of minerals and ices, right, in situ at the microscale. And you can do just the similar techniques, right, that we use for remote sensing from orbit, but at the microscale. And so, which is very incredibly powerful because now you basically are able to do petrography in situ on the moon. And so some of the objectives of the instrument, right, is whether you can use it for understanding really fundamental questions, right, about the composition, textures of this regolith and rocks, and so to help understand the geology and evolution of the lunar surface. Also understand sort of physical properties of the regolith, as well as investigate effects of space weathering. Also looking at, for example, the abundance and distribution of volatiles on the surface. And of course, being that this has similar spectral range as orbital instruments like M cubed and later with Trailblazer, right? This is something that could help for ground truth and remote sensing observations. And so this is kind of just and I don't think this is, it's hard to see. But anyway, so kind of just a little graphic showing really the instrument working, right? It is something that could go at the end of a robotic arm or on the belly of a small lander or rover, right, to really map out. And so it uses LED illumination, right? So by using this low power, active illumination, we can operate under a variety of lighting conditions, especially in shadows, right? It's not a problem. We use active adjustable focus that allows us to image over not only Z stacking, but also image near and far. And of course, then we use a visible near infrared detector. It allows us really to operate from the visible further out into, initially we designed it to go out to the shortwave infrared, but with the DALI, we're expanding it to go out into the midwave infrared, especially looking for water. Okay, so just kind of further up close, this is kind of a design. And so what AMIM can do is really combine fine scale imaging with fine scale mineralogy. And so we can resolve grains as small as 60 microns in diameter with a 30 micron per pixel. This also, of course, gives us a field of view of roughly 3 by 3 centimeters, and we can do image rough and uneven surfaces using Z stacking with autofocus as well. And of course, we would do a lot of the multispectral capabilities up close in situ. And of course, because we have that really broad spectral range, we can really detect a wide variety of minerals. And these can include igneous minerals, right, like olivine, pyroxenes, but also the presence of hydrated minerals, that might be of interest to may not quite as relevant to the moon, but of course we can see the hydration right? And so really what allows us to investigate sort of hydration of minerals on the lunar surface, especially as we go towards the poles. And then of course, detect presence of volatiles such as like H2O and CO2 ice. We even have capabilities to be able to look for potential organics if we find those in permanently shadowed regions, right? And using sort of UV fluorescence. And of course, because we have active illumination, we can really operate in any kind of lighting conditions. Okay, and this is just kind of showing a breakdown of the instrument where we have our, getting ahead here. Well, we can't really see it. Okay, so but you see the LED array panels at the front, and then of course behind that is the adjustable focus mechanism and then the detector. And so the advantage of this instrument is that the sensor it's compact that allows us to go at the end of a robotic arm, right, or the belly of a small rover. And we can do a lot of the capabilities that you normally associated with a high resolution, really large imaging spectrometer that on orbit, but this is applying it at a very small scale. And so these are sort of some of the bands that we're using. And as you can see, we have a lot of great coverage over the entire spectral range from the visible to the mid-wave infrared and targeting specific mineral absorptions that are indicative of variations in composition. And so these are just some examples of the types of mineralogy that we can see. So for example, like as I mentioned earlier, we can detect in the middle, for example, distinguish between sort of the pyroxenes, olivines, and the example on the right is if you just went out to your typical sort of camera that only goes out to 1 micron. And this is another example of using actual lunar, spectra that has been resampled to our AMIM bands. And so we can see that we can still able to distinguish between a variety of different minerals that have or that are present on the moon and in these regolith soils. And so in addition to, so here we can see, for example, we've expanded out to the 3.6 microns, and we can see that up here you have your, this is really, can't really see it. So for example, low calcium pyroxene, high calcium pyroxene, you got your olivines, you even see your plagioclase feldspars over here, those that have iron in them, but also, especially if we're looking for where there might be hematite, given that there's signatures detected from orbit, right? The instrument can also see that. Furthermore, as below, we see examples of volatiles, such as like H2O and CO2 ice, which will be really useful to understand sort of the origin of these volatiles in the permanently shadowed craters. And here I might skip, but just show that we can see a wide variety of minerals, whether alteration minerals such as clays, sulfates, and carbonates. So it could be a very valuable instrument, not only for lunar applications, but it could also even for other targets in their solar system. But of course, the real reason why motivation for this instrument is that we want to be able to detect the presence of water. And so we have targeted bands that allows us to really distinguish between the different flavors of water that might be on the surface, whether it's adsorbed molecular water or indigenous to the mineral grain, right? Whether it's like glass with molecular water in them, or hydroxyl, as well as water ice. And we can see that. And this blue line over here, it's really what distinguishes where the M cubed spectrometer cut off, right? And so you only see 1/2 of the shape of that curve, whereas with AMIM, we could see the other side. Okay, so quickly with some of the prototype that we've been developing, this is an example showing a sample from Kauai Desert in Hawaii, which is kind of a moon Mars analog. And you can really see the power on the left is sort of a natural color image, whereas on the right is a false color image using infrared bands that really highlight, really help tease out distinguish these mineral grains, and even further apply to lunar sample over here. So this is a sample collected from the Apollo mission, regolith sample. And even though it's on the upper left, you see how it just looks at a hand scale, just sort of gray, very powdery. But once you really get up to the micro scale, you can really start sort of teasing out different grains and maybe even pick out sort of the plagioclase, maybe olivines. But really going sort of on the right with the infrared, you can really start showing that differences in composition thanks to being able to go further out into the infrared. And then as we sort of expand further, you can sort of map out by individual grains, right? By pulling out sort of different end members of these pixels, and you can, distinguish then. So for example, like the low calcium, high calcium pyroxene, olivine. So all the different components that were present on the regolith, and you can map those out to really understand sort of and extrapolate sort of bulk composition of the moon. Okay, and with that, summarize, right? So AMIM is a really powerful instrument that allows you to spatial correlate mineralogy and microtexture of rocks and soils, right? It's a low power, very compact instrument, right? Very low complexity, and it really combines the capabilities of how, laboratory instruments, but also orbital instruments, but at a low mass, low power that could be used for small landers and rovers for exploration of the moon, but also could be used, for example, for other planetary exploration surfaces, for example, like Mars or even ocean. With that, thank you.